In a previous video, I implemented natural ventilation as a way of decreasing our site EUI. And so we were modeling this medium-sized office building, 125 feet long, 30 or about 40 feet tall, 3 stories, curtain walls, so a lot of glazing. And we developed a really good envelope. Passive house level insulation, very low infiltration, got to this low site EUI, but we still had a cooling load, and so I implemented natural ventilation to try to get rid of some of that, which we did. And we can see basically how that works is that um, I want losses in the summer when it's hot outside. If I can get heat losses from the building, that's good. And so if I implement natural ventilation, in other words, I'm dumping heat out through the open windows, then I can gain some energy efficiency. And it's not trivial. So if we have, so we were at 15 now with the natural ventilation, 17 without it. That's about a 12% drop in our EUI if we just as a ratio. So, so how do we do that? That's what I want to get to now. Um, the way I implemented that was with a Grasshopper script. Um, sorry. So let's open up a Grasshopper. First, let's just talk about, I don't know where we are with everybody with Grasshopper. Any questions about it? Talk to me, and we'll work it out. But just for the purposes of this video, if I haven't done this already, in Climate Studio, as far as I understand, started as a Grasshopper interface, and so what we're working with so far is really just an upgrade, a really nice upgrade that's in the Rhino main graphic window. So they have a lot of more detailed scripts that we can access, and so if we come to the Climate Studio tab in Grasshopper and open up this workflow template tool, we can just select anything we want in here. I mean, from this drop down. And so in thermal analysis, they have a natural ventilation workflow. I'm opening it. Maybe while that's opening, I should say that, this is where, if I don't say it every week, I should. We're architects. We're not engineers. Modeling can be way worse than nothing if we don't know what we're doing. Also, we have to not trust it. People can make models say whatever they want. So we are learning workflows to help us with our design process, but early and often you need to befriend engineers and learn to talk in a way that they understand and that they will respect you. So that's another way that these workflows help you. But we get into natural ventilation, it gets pretty complicated, and we don't want to assume that what we're doing is completely accurate. We're just trying to just identify trends and decide if it's worth going in a certain design direction based on what we can figure out. Anyway, so this first this workflow that I opened up has actually the full thermal analysis or thermal simulation that we've been doing. So here's our site EUI. Here's the site EUI output. There's carbon, money. So that's all the let's go back to the main Rhino page. That's all this stuff. And sorry. So anyway, we're not going to use that. We're using the new version in Rhino. What we're using is this workflow here. So I've just simplified it and kind of cleaned it up for our usage. So let me open that. Okay, so here, this is a script that I've provided for you and you can use for this purpose. Let me explain what's going on. The first thing I want to say is that this component is turned off. You have to enable it to send these schedules that we're going to build here to the libraries in Climate Studio. So actually when we save here, we will send the schedules to Climate Studio. And I have implemented this tool because I don't want to gunk up my library in Climate Studio with tons of erroneous or extraneous schedules. So I'm trying to be disciplined about it, and I would suggest you do that too. It's not the let me go back to this again. The this library system that we've been working with um, is awesome and just so useful and wonderful. At the same time, it's not completely, we can't interface with it in every way that we might want to. I've had some experience with losing templates that I save, for example. I'm not sure what's up with that. And you can't delete everything that you might want to delete. So, for example, so I'm just saying, you just be conscious of that and to be sort of organized also when you're developing anything that's going to be put into the library. Okay, so what do we have here? First thing we're doing is bringing in our weather file. So and if you don't know much about Grasshopper yet, it's basically a visual coding language. So each of these I used to be an electric guitar player, so I see these as guitar effects boxes. But you have inputs and you have outputs, and inside here is Python code, usually math, right? That's repeatable code that we can bring in and create and connect together with these little wires to create complex workflows. Um, so let's go through this one then. What we have here is our weather file that we're bringing in. So that's what this little box is for. If I right click or left click on this location, there's a bunch of preset or preloaded climate files. I've got LaGuardia here, so I'm using that one. If you were designing in a climate that wasn't in that list, you can download from, for example, the Energy Plus website. You can download to your hard drive a file and then hook this up to this input and access the file path on your computer here. Okay, then I've just converted from Celsius to Fahrenheit because everything in Grasshopper for Climate Studio is going to be in metric. They've got some workflows where they allow you to also convert. Sometimes it's confusing. So anyway, I'm going to try to keep us in IP since we're working in the US. All right, so we've got the weather file coming out in Fahrenheit, and then we have these 4 graphs. What are they? These are schedules. Well, they are data sets that tell us when the temperature outside is within a certain range. And so we can set that range here by changing these values. I've set it at 64 and 78 as typical. It makes sense that we want to have natural ventilation when it's between 64 and 70 degrees outside. If it's colder than that, we're probably not cooling. And if it's hotter than that, we're probably not going to get any cooling. So that's kind of a good range, and you can play with changing that, but that's my default. And then what we're bringing that range in, so larger than and smaller than. So when it's larger than 64, smaller than 78, we want it's both of those. Then we want to know what the data set is from the climate data. And so this is that data set. We see that most of the temperature, the hours that meet this range are at night in the summer, in the morning in the summer, and then at some periods during the spring. I mean the fall and the spring. So you see this is the months of the year down here: January, February, March, April, May, June. Yeah, I should zoom in, right? So we're saying that all the white are the times when we're between 64 and 78, and so that's when we want the windows open. And by the way, in our building, we could have this automated in terms of the windows could open automatically, or we can just say this is when we're assuming people would open the windows. So always too in simulations, getting the building to actually work the way you're designing it is a whole different question that we're not dealing with right now. Then we want the windows when the windows are closed and the temperature is not in that range. So in other words, just basically the negative of this, the negative here of this positive. Then we want the mechanical ventilation on. So we need to be bringing in fresh air when the windows are closed. So this is when the windows are closed, we're implementing mechanical ventilation. So that's another. And what are we doing here? So we're outputting these data sets as schedules that we will then implement in Climate Studio in Rhino to uh, to model when the HVAC and the mechanical ventilation, well, the HVAC system is on and when the windows are open. Okay, so we've got natural ventilation, mechanical ventilation. Then we say when we are all the data set that is where the temperature is less than 64, we want the heating to be on, and so this is that data set. Makes sense. It's winter and fall. Nothing really in summer. And then the opposite of that is when we want cooling when we're above 78. So again, the negative of this positive, all these hours are when we're above 78 and we want mechanical cooling um, available. All right, so then very simple, right? We brought in the climate data, we set our temperature set points for natural ventilation. The rest of the stuff is predetermined. And all we'd have to do then is, if I don't want to do it, if I enable it here, then it will send these schedules to my library in Climate Studio. But I've already done that. And so, yeah, so the other things that are changeable here are these titles, right? So we'll see these titles in my uh, Climate Studio library, and you can make these whatever you want. I'm doing this in New York City, so obviously then a time that I would want to implement more of these, if I have different climates, I would want to name them appropriately, and then I can have all those schedules in Climate Studio. So if we come back to Climate Studio and let's go ahead and select all my zones. Um, and I'm now going to edit them. I'm going to apply the 1960s template. So I'm going to go old school for beginners here, or to start off. And let's see, that's this one. And the reason I'm doing that is because we have nothing turned on here, so I can access all of these schedules. So if I'm in conditioning, first thing I want to do is come down. In this case, I didn't even have my mechanical ventilation on, so I'd want to turn this on, or maybe I would turn it off for 1960. I don't know. I remember that I had 5 CFM per person and I think 0.085 per square foot. Then I want to turn on my natural ventilation. And so what do we have here? We have a set point. So that's actually going to be overridden by this schedule. If we didn't have a schedule, we'd have to have a set point. So all of these are settings except for the humidity levels that are overridden by the schedule. We're only using stack-driven flow. That simply means we're just using the pressure differential from inside to outside. We're not using cross ventilation. So this is like the worst case scenario. We're saying there's dead wind and just have the windows open. So we might get a better result if we use cross ventilation, but we're not going to right now. So then I'm going to select my schedule. And here it is. Let's see, natural ventilation available. Select it. I'm going to come up to my mechanical ventilation and select the schedule for that. Mechanical ventilation available. Same thing for cooling. Cooling available. And same thing for heating. Heating available. Oh, you know what? I didn't do all the New York City ones, so I'm not actually going to run this, but, well, let me go ahead and make this correct. Because those other ones I think came with, or I didn't create those, so I guess they were already here. Let's see. So I want cooling available in New York City. Case in point, you got to be careful with all this stuff, right? And this one also was wrong. Natural ventilation. Available in New York City. And by the way, we can see here are those schedules, right? These are the same. If we go back and look in Grasshopper, this is the schedule we're bringing in. And then, okay, so let's say we're go with that. We also want to check our windows. So actually, let me open up. If I open everything up and select it all, and I edit, I just edited the envelope. But now let me, so I say, okay, it's now asking me for the windows. I'm going to change this to uh, default glazing because I'm saying this is a 1960s building. And I'm going to say okay. Then we have to do a couple things in here or just look at them. We're not going to change anything. But if we look at the ventilation settings, these are part of the natural ventilation model. We have operable area, so that means this is how much when we open the window, 80% of the square footage of that window is open, right? So we take away the frame, or if it's a double hung window, for example, you'd only get half of the square footage of the window. So zero point 0.8 means it's something other than double hung. The discharge coefficient, that's where this is another point to bring up engineers. This is a more complicated metric that has to do with data collected from actual window analysis, and it's not something that we should pretend we know what the right answer is. I'm going to leave the default, and if we wanted to get more into this, we would have to do more research or talk to somebody who's an engineer who's specializes in this. And the rest of these are for a more complicated CFD based simulation. CFD is computational fluid dynamics, and that's where we're talking about actually trying to model how the air is moving. It's going to hot air is going to rise more, and et cetera. We're not doing that. We're doing something simpler, and we're still not going to even turn our window frame on. So we're just talking about glass here. So this isn't completely accurate, but it's way better than nothing. I say okay, then I'm ready to run this simulation. I'm just going to go now to the results because I ran a number of these. Let me close this all down. Okay, so the first thing I ran was my 1960s envelope with no natural ventilation, and I got 253 kilobtu's per square foot. Then I ran it with no natural ventilation and also no mechanical ventilation. Um, Again, I don't, haven't done a lot of research recently on exactly what would have happened in 1960, what kind of mechanical ventilation they would have had. So I can set this really quickly and try both. Um, Definitely a huge difference here, right, between no natural ventilation and natural ventilation. And let's just see what's going on. We've got a big cooling load, huge cooling load here without the natural ventilation, and it's reduced when we include the natural ventilation. And why is that true? It's because we have when so when we have a cooling load here, remember these little gray bands are mechanical heating and cooling to create a balance between the losses and gains. Um, so when I change to natural ventilation, we're going to get more losses, meaning that we're taking heat out of the building by having the windows open, and that's going to reduce our EUI. We're going to be using less cooling and therefore less energy. And so we can see that's what happens. We also gain more in the winter, but we get a massive increase in anyway. Reduction in our energy usage. Maybe a more realistic, though, would be to say, um, let's say we have no natural ventilation, so we're at 248 instead of 253, because now we have mechanical ventilation with that same envelope, and then we add the natural ventilation, and we get 204. So what's that mean? And so we're talking about an old school building with single pane glass and a concrete envelope, and we said what two. No, we said 248 and 204. So 204 divided by 248, that's about 18%. That's a massive difference just by having operable windows with no shading, no other planning. Um, so clearly, in this case, that would be a very useful uh, strategy to implement, and it wouldn't necessarily change our architecture. We just have to make sure that we had operable windows, and we could also then play with other variables about how the windows were oriented toward each other. Now let's upgrade to a ASHRAE 90.1, so an energy efficient contemporary building. And again, this is better than if you're down in Charlotte, North Carolina, and you're designing commercial buildings, you're probably not designing to this standard. In New York City now, we have to go above this, but so it really depends on where you're designing. But my point of view on it is that everybody should be designing this way because it's state of the art, standard of care, regardless of what the actual law is. Anyway, um, so with a standard 90.1 envelope without natural ventilation, we have a site EUI of 27. If I implement our natural ventilation, we have 25 as our result. What does that mean? 27, oops, 25 divided by 27. It's still about an 8% or 7.5% reduction in um, energy usage by implementing natural ventilation. So it's not as anywhere near as much as it was in this one example of an old school approach to an envelope compared to a new school, but it's still very much worthwhile to consider. And we see that the mechanism is the same. Here we're going to add losses in the summer, and we don't seem to be changing in the winter, which is what we'd want because we're not trying to have the windows open then. So I don't know if that's an infiltration issue. I'm not sure, but we're being broader here. And so again, we go from more cooling load to less cooling load with natural ventilation.